Tools, education, and community to help engineers succeed. That's the new platform we're developing called the Wave. One of the key features of the Wave is called design accelerators. These are prepackaged CAD building blocks, similar to the low-code, no-code trend in the software industry, but for CAD, that help you finish new designs in hours instead of days. Download a sampling of our design accelerators for free at teampipeline.us/wave and let us know what you think. That's teampipeline.us/wave. They're free, but only for a limited time. So take advantage of this offer and download them today.
Hi, everyone. We've set up this Being an Engineer podcast as an industry knowledge repository, if you will. We hope it'll be a tool where engineers can learn about and connect with other companies, technologies, people, resources, and opportunities. So make some connections and enjoy the show.
Some of the first metal printers were essentially welders that were put on gantries or, robotic arms and stuff that were basically, automated welders. Like what you're probably familiar with, like FDM printing almost, but with metals, right? Instead of extruding polymers, you're, welding from wires and stuff like that.
Hello and welcome to another exciting episode of the Being an Engineer podcast. Today our guest is Ryan Kircher, who holds both bachelor's and master's degrees from the Colorado School of Mines in Metallurgical Engineering. Ryan has been working in the additive manufacturing industry for many years and has experience in medical devices, process validation, process improvement, risk analysis, failure analysis, and design for additive and manufacturing engineering. Ryan, welcome to the show. Thanks so much for being with us.
Thanks for having me. I'm really excited to talk with you today.
Yes, I've been looking forward to it as well. So I'll start off with the same question I ask everyone in the beginning. What made you decide to become an engineer?
It's an interesting question. And, I gave it some thought, and I don't really know, I think it was something that just always seemed to fit. I don't know if that makes sense.
It just resonated deep within your bones.
Yeah, I have some engineering friends that are like really mechanically inclined, and we're tinkering around with cars and stuff throughout high school and all that kind of stuff. I wasn't necessarily like that kind of engineer. I was more just, I loved science and math and physics and things like that. So it just seemed like a natural fit for me.
At what point did you say to yourself, yep, engineering? First of all, I understand that engineering is a thing. Like that's a role that I could make a living at, and that's what's for me.
Probably when I was, a teenager, probably like early in high school is kind of when I knew I wanted to be an engineer, I'd say.
Yeah.
Yeah.
Well, you went on to the Colorado School of Mines, and I've heard very good things about that college. What was your experience there, and how well do you think it prepared you for industry?
Well, I think it prepared you for industry extremely well. It is a unique school, I will say, though. So my number one piece of advice for anyone considering going there, make sure you want to be an engineer or something very similar, because that's about all you can study there. They have all kinds of crazy branches of engineering you can study there. You can do explosives engineering, mining engineering, metallurgical engineering. But it's a very engineering focused school, which if I had to make one criticism of it is that it is almost too focused on engineering. So like when I got out of college, I'd be talking with friends and stuff who went to other schools, and they would talk about like, history of art and all these really interesting courses they took, and I didn't get to take any of those at School of Mines. Very
interesting,
very like math and physics and all those types of things, right? Like, I mean, we had to take a philosophy class, and it was actually called the philosophy of engineering. So it was like whether you should build a bridge or a dam or not, and those types of things. So it's a very focused 4 years. It's pretty challenging too. Definitely, some hard courses and things like that.
Not a whole lot of arts and humanities, though, huh?
Not a lot of arts and humanities. Not a lot of. I mean, it's never going to win awards for its partying and social aspects either, right? It's a lot of kind of nerdy engineers, right? I actually went there when it had its peak of female enrollment, and that was 30%.
Oh,
And surprisingly,
wow.
it's actually gone downhill since then.
Interesting.
Yeah, yeah.
Huh. And you said it was a pretty challenging coursework there, huh?
Yeah, yeah. I mean, a lot of very bright people go there, and a lot of the first semester, like that first like test that we have to take. I think it's an eye opener for a lot of students, because a lot of them kind of coasted through high school, or didn't really have develop good like study techniques and things like that. And yeah, after that first like chemistry test, kids are walking around kind of glazed eyes and like, what just happened? Because it's, yeah, I definitely had to learn how to become a student much better when I went there.
I think that's one of the best things about engineering school in general is it teaches you how to learn, and maybe even more so at the Colorado School of Mines.
Yeah, I mean, I definitely took tests when I was there that the professors would tell you when they handed out the test, you don't know enough information to fully answer some of these questions. I just want to see how far you can get.
Interesting.
So, yeah, I mean, it really does like force you to kind of try to think and learn and, try to solve problems even when you don't even know enough information to fully solve them. So
yeah, stretch yourself a bit. That's cool. Well, you've been working in metal additive manufacturing for quite some time now. I think most engineers are pretty familiar with like polymer-based additive manufacturing, 3D printing, but probably a lot of us aren't super up to date with the current state of the art of metal additive manufacturing. Can you just kind of recap where we've been in the past 10 years in regards specifically to metal additive manufacturing, and where we are now, and kind of what advances that we might look forward to in the next 5 years or so?
Yeah, I mean, there's a variety of, just like with other additive techniques, there's a variety of different techniques that people use to additively manufacture metals. There's, at a very basic level, some of the first metal printers were essentially welders that were put on gantries, or, robotic arms and stuff that were basically, automated welders, like what you're probably familiar with, like FDM printing almost, but with metals, right? Instead of, extruding polymers, you're, welding from wires and stuff like that. But I've spent the majority of my career in powder bed fusion type metal printers. There's a variety of different ways of doing that as well. But the essential process is, you start with some sort of base plate or substrate, and distribute a very thin layer of metal powder, and then use an energy source. The two most common are either lasers or electron beams, to essentially weld that layer of powder to the substrate, and then the substrate drops. You put down another layer of powder, and you weld on top of that. So it's called powder bed fusion because it's a powder based process, and you print thousands of small layers of that powder on top of each other.
So it sounds a lot like SLS, but with metal.
Yeah, yep. I think the big distinction there, and this wasn't always the case, but it is primarily the case now, is that we're not necessarily sintering the powder particles together. We are really essentially creating a weld bead, right? So that powder gets turned into a liquid and then solidifies. So you're getting, fully dense material if it's done right.
Interesting. Okay.
And then as far as like advancements, right now there's kind of an arms race as to who can put the most lasers or maintain the most weld pools at the same time. People are getting pretty creative on how they're doing that. So that's kind of where the industry is improving right now. Just trying to put as much energy into that powder bed as possible to speed the process up. Because right now, one of the biggest drawbacks to powder bed fusion is it just takes a long time, right?
Give me a sense for how long that takes. Let's say we're printing like, I don't know, a baseball sized part that is not solid. Maybe it's like a 30% infill or something. How long does that take to print in metal?
Like a day, right? But you could probably fill a build platform full of like, I don't know, 20 or 30 of those, and it might take 2 or 3 days.
Okay.
So there's definitely, like, it's not FDM is kind of really based on how much material you're laying out. Metal-based processes are really kind of driven by how tall the parts are, right? The taller the parts, the longer it takes to build them, because there's a whole step of distributing that layer of powder that you have to do every single layer. So that can start adding up over time, right?
Yeah.
So it can really drive the build time.
Okay. And so metal 3D printing it takes longer for sure than like FDM or SLS, but it's not like 10 times longer, right? It's, I don't know, 2-3 times longer, if that. Is that true?
That's an accurate statement, right? I mean, and with all the lasers and stuff, it's getting close to, I mean, it could be faster than some of those other additive processes as well, with some of the newer improvements that people are making. But, the bigger competitor that it's dealing with is conventional manufacturing, like machining or casting or something like that, right? Can it compete on a scalability and a efficiency side, like comparison to those types of processes, right?
Well,
that's where it's a struggle.
What are some of the biggest limitations right now? I mean, time, it sounds like, is one. Is that the biggest limitation, or are there others as well?
I mean, time and cost. It's expensive. I mean, the systems that we're using to do this are expensive. There's some like entry level, like R&D type systems you can maybe get for $100,000. But most of like the industrial additive systems we're using are $800,000 all the way up to, for some of the ones with multiple lasers, $3 or $4 million. Right. Wow. So they're expensive pieces of equipment that you have to depreciate. And if they're slow, you might need a bunch of them to be able to make, if you have to make 10,000 parts a year or something like that, all of a sudden you have to have a bank of the systems, a lot of upfront capital cost. So it's other limitations. I mean, there are other metal processes that can make nice, real fine, detailed, precise parts, but the powder bed fusion process is kind of limited in its resolution by the powders that we're using. And the challenge there is that they need to be able to get distributed well. So like flowability of the powders can be challenging. So there's kind of a limitation on the fineness of powder we can put into the processes, which kind of relates to the kind of details we can get. And then I think one of the other, I wouldn't say it's a limitation, but one of the kind of downsides to metal additive, at least with powder bed fusion, is that any support structures or things like that you have to build onto the parts are made out of metal, right? So removing
can't just snap them off.
Exactly, right? They can be really challenging to remove. A lot of manual labor, chisels and pliers and stuff like that, right? And so it's kind of the dirty, dark secret of metal additive, especially like in medical devices, which I've focused on a lot. Most people that are doing metal additive have a core group of people who spend their days removing supports off of parts.
Wow. Okay.
Yeah.
What are some applications that metal 3D printing can be used for that maybe a lot of engineers aren't familiar with or just haven't had exposure to?
Everyone always wants to like swing for the fences and build like a bracket to put on a satellite or, a rocket engine or cool implants and stuff like that. Those are all very high-end applications, right? And the testing and qualification or validation you have to go through to be able to use those parts is quite extensive, can take years, right? I still think metal additive has a lot to offer in manufacturing tools, right? Like a really cool application that people are using metal additive for is to make injection molding tools, right? So your ability to put like conformal cooling channels underneath and inside an injection molding tool enables you to cool down that tool much faster than you could if you were just like drilling cross holes and stuff like that, which is what people typically have done and still do. And that can have an impact of decreasing the cycle time by, 20 or 30% or something. Taking a couple seconds off of each shot of your injection molder, which can have huge payoff, right? And at the end of the day, if the tool breaks, you make another one, right? It's a lot more reward for a lot less risk, right?
Oh, that's interesting. I wouldn't have thought of that. I mean, that's a pretty big part. Are large parts like that, tool-sized parts, commonly made?
Yeah. I mean, that's another. I mean, we talked about the arms race as far as putting more lasers on systems, and it kind of goes hand in hand with the arms race of trying to make bigger and bigger parts, right? Because if you have one laser trying to make a gigantic part, I mean, you're literally thinking it could, that system could be running for a month, right? So that's why people are putting more lasers on the system, is to try to get that build time down to a reasonable number, like a couple days or even a week, right? So the biggest systems out there, they can print things that are like a meter cubed now, right? Or even bigger, some of them. Some like specialized systems.
Gigantic.
Yeah, mostly. And those are mostly being used to. It only makes sense to use a printer that size if you have to make a part that's that big, right? So like what we do with making, spinal implants and medical devices, the trade-offs, the extra expense and difficulty of using multi-laser systems with big platforms just isn't there. So we still like to use the small ones. They're more agile, more predictable, simpler.
How about the surface finish? I mean, you talked about using these to make molds, but on a mold, you have to have pretty nice surface finish. And last time I checked, which admittedly was several years ago, the surface finish on metal additive is kind of rough. Is it just you have to go through a post-processing phase and buff that out?
Yep, exactly right. Almost, I mean, it depends on what you're trying to accomplish. Like some of the medical devices that we make, people like that rough surface, right? Because bone actually likes that rough surface. So, in those situations, that rough surface is one of the reasons people are using additive. But almost everything we make at RMS, we go and machine or finish surfaces that need to have a higher finish, right? If they're mating surfaces, things like threads, things that are going to get laser marked or labeled or something like that. So almost everything we make in our additive systems actually goes into a CNC mill.
Okay. Interesting. Yeah. Can you give us, I don't know if there even is a kind of a rule of thumb for cost of making metal additive parts? If you're going to make a part metal additive versus the same part out of like a die casting or a machining operation, how do those compare?
I used to have a rule of thumb that if you can make it another way, it's probably going to be cheaper. I mean, ultimately, so it's expensive, right? We're making one product right now that is actually proven me wrong. It's a titanium thin-walled housing for a medical device instrument, where it's the bar stock that you need to use is you end up throwing away 90% of that bar stock to get to the housing, right? And titanium's an expensive material, so that's the one case where it's actually more cost effective to use additive. But in general, if you can make it another way, it's likely going to be more economical right now. There are some other metal processes coming up, like binder jet printing, that maybe are changing that. Those systems can make 10,000s of parts a day. So the economics there are pretty lucrative, right? The automotive industry is finally starting to look at metal additive because of binder jet printing, because it is high throughput and low cost. But like powder bed fusion is pretty pricey. So when it comes to trying to decide when and how to use metal additive, unless the part is designed with some sort of extra value in it that can only be manufactured through additive, the economics usually aren't going to work out.
Got it. Okay. How about designing for metal additive? Is it fundamentally the same as designing for, like polymer-based 3D printed parts, or are there any special best practices to follow?
It's similar, right? It's mostly, I would say, it's mostly similar to FDM, right? So the tricky thing with there's tricky the tricky thing with metal additive is that it's a pretty hot process. So you have to support parts, and you have to support parts for usually one of two reasons when you're using metal additive. One, you have these down-facing surfaces like you have an FDM, right? Like you're just fighting gravity. You got to have something there to support it. The powder bed itself isn't necessarily enough support. So you have those kind of supports that are just basically scaffolding and stuff to kind of give you a platform to build on top of. But then you also have what a lot of people call solid supports. And I like to consider those more like anchors, right? Those are there to actually hold the part in place because it gets so hot when you're printing certain areas that you build up a lot of residual stresses, and the part can warp outside of the build plate, crack, all kinds of things, right? So there are some additional like support strategies, things you have to take in consideration when designing for metal additive. And all of those are things you got to go remove, right? So a big thing in metal additive is trying to figure out how to build the parts without any supports, right? So that comes down to certain geometries that can print well, certain angles that you have to avoid and things like that. And then the industry's getting really creative with different processing parameters, maybe scanning a layer with less power and then coming back and then welding it. And the whole goal there is to kind of develop what people are calling like supportless processing parameters that allow you to open up that design space so you can print geometries that typically would have required supports without supports. That's kind of a big, from a software and like process standpoint, that's like a big area of focus right now in the metal additive.
So I thought that I'm just going to go out back to the pseudo analogy of SLS because that's what I know. I don't know metal hardly at all, but in SLS you don't really need supports at all. I thought that the powder based metal additive was a pretty similar process fundamentally, but it sounds like that's not the case.
Not the case. Definitely not the case. Just because of the warping and residual stresses. And it's not that, like I said, fighting gravity, that's not really the right word. It's more, you want to try to keep it in place. You got to hold it in place. It wants to come popping out of the build plate and warping up, thick potato chips and things like that, right? And then the problem is then it comes and destroys or hits the rake or distribution arm that you're using to move the powder around. And then bad things happen.
So it does look like a bed of powder as in SLS, but the like the thermal stresses going on are so intense that this thing is just moving around a lot more than like a polymer part would move.
Yep.
Okay, got it.
Unless it's held in place, absolutely, yeah.
All right. How about the purity of the final product? I mean, if you print something out of titanium, is it going to be like pure titanium, or there's some kind of fillers that are part of that powder that end up in the product as well?
So as far as powder bed fusion, the laser based and the electron beam melted, the electron beam based processes, what you put in is more or less what you get out, right? There are some intricacies to that because you are creating a weld pool. Just like in welding processes and stuff like that, you got to use shielding gases, right? And the shielding gases are there for a couple reasons. One is that they do maintain that chemistry of that metal powder when it's in its liquid form. Prevents it from picking oxygen and stuff up from the air. But they also move spatter and debris away from the weld pool too. So generally, most metal-based powder processes have argon or nitrogen gas that's introduced and then actually pushed either through fans or manifolds or something like that across the build plate. So if you're ever looking in a metal additive system, usually you can kind of see like a plume of smoke and debris kind of getting pushed into the back or the side of the machine out of the way.
I hadn't even considered that before. So the what did you call it? The gas shielding?
Yeah, shielding gas. Mm-hmm.
Shielding gas. Okay. Is that's just to create a barrier around the part so that it doesn't oxidize or start corroding?
Yep.
That's okay.
Well, that and to move the debris and stuff away from, because that debris will detract from the laser or electron beam, right? So they kind of do different things in the two processes. Electron beam melting is typically done under a relatively high vacuum because even argon gas, I mean, it's basically electrons, flying from the top of an electron gun down into the powder bed. So they'll get distracted by essentially anything. So that process is actually done under a high vacuum with just a small amount of helium, actually, because they have to use a really light gas so that it doesn't detract from the energy.
Well, I'm starting to realize why some of these machines are upwards of $1 million. There's a lot going on.
Exactly, right? Well, and then the shielding gases can get expensive too, right?
Yeah. Okay. Yeah, that's just another consumable, I suppose. Right. All right. Well, let me take a very short pause here and share with the listeners that teampipeline.us is where you can learn more about how we develop medical device and other product engineering or manufacturing teams develop turnkey equipment, custom fixtures, and automated machines to characterize, inspect, assemble, manufacture, and perform verification testing on your devices. We're speaking with Ryan Kircher today. Ryan, so we talked a little bit about the cost for metal additive machines, anywhere from like $100,000 up to several $1 million. How about the space? I mean, there's obviously a capital investment that goes into there, but how much space do these things take up?
A decent amount, right? And it can vary from machine to machine quite a bit too. And then, I mean, it's not just the printer. You got to have equipment to, receive and reprocess your powder to get it ready for the next build. You got to have somewhere to take, the parts off the build plate and all that. So it takes up a lot of space. I mean, the printers that we use at RMS probably take up like a 5 foot by 5 foot area. Right?
How tall are they?
Those systems are probably 10 feet, 12 feet tall.
Okay. Wow. Yeah, that's
I've definitely heard about several situations where people have bought a metal additive system and then have not been able to get it into their lab because it's too big for the door frame.
Yeah, 10,
several doors have been removed.
Wow. Jeez. Huh. Yeah, it's a lot cheaper at that point probably to remove the door than it is to send the equipment back.
Yeah. Most of them have vacuum chambers or something else too. So, I mean, big chunks of metal too. Right. So heavy. Yeah. A lot of times people have to worry about the floors that they're getting put on as well. So, I know medical is one of the primary industries in which metal additive is being used for like orthopedic implants, especially with the rough surface area that facilitates bone growth, things like that. Are there other industries where you're seeing a lot of success with metal additive? I think one of the probably like the cooler applications that's getting a lot of press and stuff right now is space exploration, right? So one of the nickel-based alloys are actually relatively weldable and are really good fit for metal powder bed fusion. So and they're used a lot in in some pretty high temperature applications in rocket engines and stuff like that. So you're seeing a bunch of those types of companies, even like small little startup companies that are creating launch vehicles and other things like that, latching onto additive for their ability to make some pretty impressive components that are big and very intricate, with all kinds of conformal channels through them and things like that.
Yeah. What's the biggest metal additive part you've seen made?
Oh, I mean, pretty big. I mean, the biggest parts I've seen aren't made in powder bed fusion. They're typically made with that welding process I was talking about, which we call directed energy deposition, DED. Where you're basically using a wire welder on a gantry or a robot. I mean, some of those parts can fill a room. They're pretty big.
Wow. What kind of part is that would fill a room?
So I worked at Lockheed Martin for a handful. I wouldn't say a room. I mean, I worked at Lockheed Martin for a couple of years, and they were making, fuel tanks with the DED type process. I mean, some of those had diameters of, I don't know, probably 4 or 5 feet at least, right? Really cool application. Replacing some really expensive like
Wow.
castings and forging type process. Products that had like lead times of a couple of years. So they were using additive because it cut down on delivery time, right?
Wow, that's really cool. Well, let's see. So we've dug in deep to metal additive, and that's been super interesting. But I also wanted to touch on the fact that you run your own consulting business on the side. I'm curious to learn a little bit about how that started and kind of what your focus is there. Is it also metal additive?
To be honest with you, I do have a consulting company. It's kind of in what I would call kind of a dormancy stage. I work full time for RMS company right now, so it's mostly kind of a side project, kind of a side hustle, where I only do certain projects with basically the goal of kind of networking, working with some colleagues in the past and stuff. So I'm kind of picky about the projects that I work on. It's mostly stuff that is just super interesting to me or people I like to work with. So I only find time to do it. I also have like an infant daughter. So balancing a full-time job plus her is enough. So the consulting's kind of taken a backseat over the last couple of days. I started it about 4 years ago. And that was my full-time job for about a little over a year. Oh, wow. And RMS company was one of my customers. And I just really enjoyed working with them. And the list of projects that we had to work on was so large that they're like, why don't you just come work for us full time? RMS company is based in northern Minneapolis, and I live in Colorado. And I mean, it's a giant machine shop, right? We have 700 CNC mills, 30 additive printers. So the concept of like somebody working remotely for a big machine shop was kind of laughable 3 years ago, right?
Yeah.
But the pandemic if there was a bright side to the pandemic, it's that it made it fathomable that I could work for RMS remotely, and it's been working out really well for me. I really like it. But before that, I was doing the consulting full time, and if anyone would ask me like 10, 15 years ago, like, what do you want to do with your life? I always told them, eventually I'd like to just be a consultant and do my own consulting thing. I'm not sure if I feel the same way anymore. It can be kind of stressful.
Oh, what's changed?
Well, I mean, just owning. I mean, I don't need to tell you, but like owning your own company comes with a lot of other baggage, I guess you could say.
Yeah.
Doing the financial part of it, how to do things like get insurance, just a lot of things to learn. It's half running a company and half doing what you're supposed to do, right? So it takes a lot of time just to have the company, set up and doing all that kind of stuff. So you don't have as much time left over to do the actual consulting, which is where you make your money. And I don't know, for me, it was a hard balancing act with trying to keep a workload that was manageable, but also ensure that I had work in the future, right? So it was this, and most people want, if they're interested in talking to me about consulting, they have a problem that they want to solve now, right? So it was hard. You had to turn people away because you were too busy to do the project for them immediately, and they weren't really interested in waiting 6 months to do it. So they'd have to go find something else to do, some other solution. So I kind of had to like manage it like kind of like an investment portfolio. I had like not necessarily the highest paying consulting gigs, but ones that were either like retainer type things or like a consistent 10 or 15 hours a week that I knew I was going to have for 6 months. But then I'd have to keep some time open so that I could do something at the last minute, stop what you're doing and work on this relatively full time for a week type thing. So it was just kind of this balancing act. And it can kind of be stressful,
For sure.
Kind of not knowing if you're going to have any work in 6 months type thing.
Yeah, I know what you're saying all too well. Someone told me a long time ago, this was at the point where I was starting to hire people, but I was still also doing a lot of the work myself as well. And I think I was probably complaining to someone. I was saying, I really need to focus on building the business, but I can't because I'm spending so much of my time actually doing the work, And it was suggested to me that, a lot of times what happens is the owner kind of stops doing the technical work and just focuses on building the business. And that's one solution. But another solution that isn't so common or popular is that you could hire a president to run the business so that you can spend most of your time, working in the technical area of the business. And I thought that was a really interesting approach that I never would have thought of myself. Turns out I kind of like working on the, building the business side. So it's worked out well for me. But for others who might be listening to this, that is an option. Just hire someone to run the business so you can work in the technical side within it.
Yeah. Before I was doing consulting, I was kind of in a director manager role of a team of engineers. And I think, that role plus the consulting has helped me kind of realize that I really like being an engineer.
Yeah, right.
And when in college, someone told me that, 75 to 80% of engineers aren't actually doing engineering after 5 years or something in the field. They're a manager or something else or whatever. I guess I'm one of those rare exceptions. Whenever I have a performance review with my boss, he's like, what do you see yourself in the future? And I'm like, at Lockheed Martin, they had a phrase for it, an individual contributor, right? It's everyone's always trying to force you up into management roles and all that kind of stuff. Right. And that's kind of, I don't know. I think we've been kind of programmed to think that if you're not getting, if you don't have manager, director or whatever in your title, that you're not success, that's kind of the label of success, right? So yeah, they have this other track that's for the individual contributor, the guy who just wants to be an engineer for his for his career.
Yeah.
Yeah. And it's weird. No. It's kind of seen with kind of I don't know. It has a stigma to it almost.
I agree, 100%.
Totally okay with it.
Unfortunate that stigma exists, I think, but I think that's a totally very respectable and honorable approach to being an engineer, is to just be a really good engineer. And that's what you do for your whole career. That's great. There's nothing at all wrong with that. Frankly, I think that we need more of that type of role, because a lot of engineers, they get promoted to being a manager and, turns out you're not a great manager, but no, but you're there anyway.
Most engineers I know have horrible, emotional EQs, they're not right.
We're probably the worst suited group of people to be managers.
Yeah. I remember sitting in a leadership training course, and they kept using the word empathy. You need to have empathy for all your employees and stuff. And I don't hope this doesn't make me sound like a horrible person, but I was like, I just don't know if I'm really capable of having genuine empathy for a bunch of people I work with. And I guess I don't expect people to have a lot of empathy for me either, I'm a little old, I guess, but work to me is a little, I think the workplace has definitely kind of changed over the last 20 years, but I'm one of those, go there, get my work done, and maybe have a couple friends at work, but it's kind of different these days.
Yeah. I think, had it not been for marriage, my level of empathy would probably be even lower than it is today.
Oh yeah,
I learned a lot more in marriage about that than at work.
And then having a kid, that changes you too.
It does.
Maybe that's part of the reason is that I never had kids until just recently. So, when I was 20 and 30 and stuff like that, I never really developed those skills. I don't know.
Well, you've got a wild ride in front of you. I'm ecstatic for you.
It's been a wild ride already, so it's pretty exciting.
All right. Well, Ryan, anything else that you think we should cover that we haven't hit on yet?
Not really. I don't know. I would say one thing that I've kind of also realized over the last couple of years that's kind of a shift is that earlier in my career, which I think is perfectly fine, I wanted to learn everything, and B, like, I wanted to know about every single additive manufacturing process and all the different metals, all the different applications and stuff. And I wanted to, understand the aerospace industry, the medical device industry, the industrial industry, all that stuff. And I've kind of come full circle, because I started in additive making medical devices, and then I kind of branched out and did all this other stuff. And I've realized recently that, like, I think I'm perfectly okay trying to be at least really good at making medical devices and with additive. It's kind of, I don't know, like, to me, it seems like maybe I'm not branching out enough anymore, but I don't know. I think a lot of people these days like to keep moving careers and doing different things and stuff. And I don't know, I've kind of come to terms with it. And I like just kind of focusing on trying to do one thing really, really well.
I think that's great. Yeah, no, it makes total sense to me. I agree with that philosophy. There's a quote I have on my wall by, I think it's the author Ben Hardy, I think, Deep Work, the author of that Deep Work book. And it says, I'm not sitting in my office right now, so I might butcher it a little bit. But basically it says, success is easy. It's all about taking 20 steps in one direction. Most people take one step in 20 directions. Which I think gets to the heart of, what you're saying. Get really good at one thing and do that thing. And everyone's different, Some people would maybe prefer to know a little bit about a lot of things, but I think there's just a lot of value in being really good at one or two things.
Yeah, I think I'm just like naturally very curious. So I always kind of want to learn about everything else. But just trying to focus on one particular thing is what I'm at least working on right now. So
yeah. Great. Well, Ryan, thanks so much for joining me today. I sure appreciate it. How can people get a hold of you?
You can look me up on LinkedIn. I'm Ryan Kircher, and there's some other Ryan Kirchers out there in the world, but I think I'm the only engineer that I've been able to find so far. So I think that's probably the easiest way, LinkedIn.
Perfect. All right. Well, Ryan, thanks so much. Appreciate your time with me.
No problem. Thanks.
I'm Aaron Monker, founder of Pipeline Design and Engineering. If you liked what you heard today, please share the episode. To learn how your team can leverage our team's expertise developing turnkey equipment, custom fixtures, and automated machines, and with product design, visit us at teampipeline.us. Thanks for listening.